This section is called Lagrange Multipliers. The goal is to solve constrained optimization problems using Lagrange multipliers. This is why people are afraid of math. Look at all those scary looking words in that one sentence that describes the goal. So really what we want to do is, given a particular domain for a function, usually z equals f of xy, so a surface in space usually in this section, not always. Given a particular domain, we want to find the maximum value on that domain and the minimum value on that domain. And it will be an absolute maximum and minimum, absolute extrema, if you want to put it all in one word, on that constrained domain. Hey, that sounds like a good name for a band. We're the constrained domains. Yeah. So let's think about the level curves of a generic function f. So the level curves, pretend like we're zoomed in on a function, and pretend like these guys represent the level curves of some function f. So this level curve right here might be associated with f equals a height of 8. So that's like the z value of 8. Oh, no, you know what? Let's do it this way. Let's go from lower to higher. So let's go 2 for that one, and then the next one we'll say that this level curve is what you get when you set z equal to, say, 4. And this level curve is what you get when you set z equal to, say, 6. 2, 4, 6, 8. Who do we appreciate? Mr. Chamberlain. Mr. Chamberlain. Okay, so as you look at it from, I guess, here, I guess you're traveling, if you start here and you travel in, say, the northeast direction, you're kind of going up, right? In fact, let's create a curve that does that. This is going to be our constraint curve. Let's create a curve in the xy plane that at least, it doesn't have to start here, but that's where we're going to start looking at it. And maybe it goes like this. This is all happening in the xy plane, and it's a nice smooth curve. Maybe it goes like that. I'm not going to draw the rest of it yet. Let's suppose that on that constraint curve is going to go further, and on that constraint curve, f is going to reach, let's say, an absolute maximum of 6 at, say, this point. So in the xy plane, the ordered pair, let's say that point is x naught, y naught, and that's the ordered pair, and I'm going to draw it so that that curve in red intersects x naught, y naught, so that x naught, y naught is on that curve in red, and if you plug x naught, y naught into the function, in other words, take f of x naught, y naught, you're going to get an absolute maximum on that restraint curve, on that constraint curve. So let me write that down. So suppose f of x naught, y naught is, let's keep it local for now. Let's keep it local. It will actually turn out to be an absolute max, but let's say it's local. Is a local maximum on the constraint curve on G. Okay, what's G? Okay, G is this guy. This is G of xy equals some constant, or it could be 0 if you just think of the constant as being part. Bring it over to the other side, and you'll see it written both ways. Or G of xy equals 0. You'll see it written both ways. Doesn't matter. So but we'll stick with the first way. Okay. So I'm going to continue drawing that curve in red, G. What's it going to have to look like when it intersects the level curves of f in blue? What's it going to have to look like? How is it going to intersect? There's only one. It can only intersect the curve in blue, which is a level curve at 6, since we know that the local max occurs there. It's got to be tangent. Think about it. If it's not tangent, if it were to go through like this, well, we're really zoomed in. The function's increasing if you go that way. So there's no way that f of x naught, y naught is an absolute max if this constraint curve passes through the point that produces the max like that. Because if you take f of any of these values over here, you're going to get higher values closer to 8 than 6. But we're already told 6 is the highest it can get. So no, that can't be true. It's got to be tangent. So it's got to hit it and then back off a little bit, right? That's how it has to look. And because of that, we can develop a method for finding these values, x naught, y naught, such that you get a local max or even a local min. A similar picture could be drawn for that. So why? What has to be true then? Well, let's look at gradients. Remember gradients, del f, del g? Okay, del f, there was a particular property we talked about last time in the sixth section, 14.6, right? We know that del f is normal to its level curves, right? So del f, I can be very confident that del f, do del f in green, del f, I can be pretty confident it points, I don't know how long it is, but it points in that direction. In other words, this would be a right angle with the level curve and actually with g right there as well. Because you could look at that curve in red as a level curve of the function z equals g of x, y. So this arrow here is a representation of del f. Del g, now I'm not sure which direction del g points in, but I do know it's going to be perpendicular to the curve in red at that point of tangency and any other point as well. But that makes it parallel with del f as well. So del g could go, I wanted to do a different color there. Hold on. Del g, let's do del g in purple. And del g could point this way, I don't know how long, or it could point this way. Either way, it's going to be perpendicular to its level curve in red, right? Which means it's parallel to del f, which means it's perpendicular to the level curve in blue as well. So let's say for the sake of argument, it points like that. So that guy in purple is del g. So the point here is that del g is parallel to del f, which means those are vectors, right? And by the way, these are vectors evaluated at x naught, y naught. And usually I put that in, but I'm being fairly informal here. I'll be more specific below. I wrote out the statement already for you. I just want you to comprehend it before we go over the official language here. What does it mean when two vectors are parallel to each other? Yeah, we'll make it the same thing, equivalent anyway. We'll say del g is a scalar, del f rather is a scalar times del g. And guess what we use? We use this Greek letter lambda. Looks like half an x, or part of an x anyway. So del f is equal to lambda times del g. Okay? When you say two vectors are scalar multiples, or parallel, they are scalar multiples. Parallel vectors are scalar multiples. So we can write it like that. Okay, so what did we just develop here? Well, here's the official wording, I suppose. So assume x naught, y naught produces a local extremum, so I generalized it. It could be a local max or local min, of z equals f of x, y on the constraint curve given by g of x, y equals c, where c is a constant. Note that both del f evaluated at x naught, y naught and del g evaluated at x naught, y naught are normal to the level curve of f at x naught, y naught. That's what we just developed above. So del f is parallel to del g at x naught, y naught, and thus, I already blew it, del f is equal to lambda del g for some scalar lambda. Lambda a scalar. Okay? That scalar is going to be called a Lagrange multiplier. Note number one, exactly what I just said. Lambda is called a Lagrange multiplier. Number two, on the constraint g, the extrema turn out to be absolute. Number three, assumptions. These are assumptions that must hold true in order for what we went over above to work. F is differentiable, which means simply for our purposes, it means it's really a well-behaved surface, okay? If it is in fact a surface. And G is a nice smooth curve. If you have a cusp somewhere on G, that ruins things. The other thing that could ruin the method that I'm about to present, del G can't equal the 0 vector. It could turn out that del F evaluated at x naught, y naught equals 0 when lambda equals 0, however. It's okay for lambda, the Lagrange multiplier to equal 0, but the method I'm about to present is going to fail if del G at that point of interest is equal to the 0 vector.